You are welcome to the GMAT41's YouTube channel. In this video lesson, I will be teaching you the concept of electrolysis. Specifically, we shall give attention to Faraday's two laws of electrolysis. However, before we move on into Faraday's laws of electrolysis, we would like to get a preview of what electrolysis is, and the concept of electrolytes as well as electrodes. When we talk about electrolysis, the whole idea is using current to bring about a chemical change. So you say in this case, you are going to introduce, your direct current into an electrolyte. The electrolyte is a solution that conducts electricity. Then what will this current do? The current will cause a chemical change in that electrolyte by decomposing the electrolyte. The electrolyte can be in its molten state, or in aqueous form. So simply put, we define electrolysis as the chemical decomposition of a compound in its molten form or aqueous form as a result of passing direct current into the solution. Now, while explaining the concept of electrolysis, I also give attention to what electrolyte is. It is simply a solution that can conduct electricity. A good example is copper 2 tetraoxosulfate 6 solution. Another one should be ammonium chloride solution, sodium chloride solution. These solutions, they conduct electricity, either in their molten form or in their aqueous form. Now when current passes through this solution, what happens? The solution will be decomposed, will be dissociated, and the ions will start moving from one point to another. These points where the ions move from and to are called the electrodes. They are called the what? Electrodes. So this brings us to the concept of electrode. And so we want to ask, what is an electrode? An electrode is a terminal through which current can either enter or leave a solution. Now, this electrode can either be positive or negative. And so we have the anode and the cathode. Please take note of this point, because although this video focuses on electrolysis and where we make use of the electrolytic cell, are you following? Because during this electrolysis process, the cell that we use in carrying out this process is called an electrolytic cell. Now we have that which we call electrochemical cell. Electrochemical cell is also called Voltaic cell or Galvanic cell. The reason I'm making reference to this is because I want to explain the concept of anode and cathode. Now we'll focus on the anode and the cathode as electrodes in electrolytic cells, since this lesson is based on electrolysis. When we are talking about electrolytic cell, and we explained already that electrodes are terminal through which current can enter or leave a solution. We have the positive electrode in electrolytic cell. Now the positive electrode in electrolytic cell is called the anode. It's called what? Anode. So the anode is the positive electrode in electrolytic cell. Then the cathode is the second electrode. The cathode is the negative terminal or the negative electrode in an electrolytic cell. So don't forget that. We have two types of electrodes, the anode and the cathode. Now when we are talking about electrolytic cell, the cell where electrolysis takes place, the anode is the positive terminal and the cathode is what? The negative terminal. Good. This now takes us to the concept of electrochemical cell or voltaic cell or galvanic cell, like I explained already. Since I mentioned that, I would like you to take note of these regarding the electrodes of electrochemical cell. But once again, as a quick summary, you want to get this idea of electrochemical cell. In that cell, chemical changes are used to produce current. So do you get that? In an electrochemical cell, you are not sending in current into the solution. No. In this case of electrochemical cell or galvanic or voltaic cell as we refer to it, you have chemical changes that produce current. That is where our battery, comes into play. So in an electrochemical cell, we also have the electrodes, the anode and the cathode. But now, what is the difference in the sign convention of the electrodes in the electrochemical cell and the electrodes in the electrolytic cell? For electrochemical cell, voltaic cell or galvanic cell, the anode is the negative electrode. Please take note of that. The anode is what? The negative electrode. That's correct. Therefore, it leaves us to say that the cathode of electrochemical cell is the positive electrode. So don't forget this, please, because the examiner can use that to ask you a question, in comparing the sign conventions for the electrodes in electrochemical cell and the electrodes in electrolytic cell. Once again, let's go. In electrolytic cell, the anode is the positive terminal. In electrochemical cell, the anode is what? The negative terminal. In an electrolytic cell, the cathode is the negative terminal, while in an electrochemical cell, the cathode is the positive terminal. During electrolysis or electrochemical processes, redox reaction takes place. Then, in one of my videos, I have talked about the concept of redox reaction, that is reduction and oxidation. Because these are complementary reactions in any chemical process. Now, it's important for you to know that in both cells, whether electrolytic cell or electrochemical cell, oxidation takes place at the anode, while reduction takes place at the cathode. That is in both cells, okay? In both cells, what happens at their anode is the same, which is oxidation. And what happens at the cathode is the same, which is reduction. And of course, as we know, reduction is gain in electron. And when reduction occurs, which leads to a gain in electron, what would be the overall effect on the oxidation number? The oxidation number of that species, be it, a metal, as the case might be, the oxidation state will reduce, even if it's non-metal. A gain in electron will lead to what? A reduction in oxidation number. So when we say that reduction takes place in the cathode of both cells, it means that at the cathode, we expect reduction to occur, and when we say that reduction is occurring, whatever is going to the cathode there is gaining electrons. And when they gain electron, the overall effect on the oxidation number is a reduction in the oxidation number. What happens at the anode? At the anode of these two cells, electrolytic or electrochemical cell, oxidation takes place there. Oxidation takes place there at the anode. And what is oxidation? Oxidation simply means a loss in electron. And when electrons are being lost, what is the effect on the oxidation number? The oxidation number of that ion will now increase in that case. Take note, loss in electron takes place at the anode of both cells, and that is oxidation. And this leads to an increase in the oxidation number. This is wonderful. Having given a general view of electrolytic cell and of course, a kind of partial knowledge of electrochemical cell, we shall now draw our attention fully into electrolysis. Like I said, this video will deal with Faraday's laws of electrolysis specifically. I hope you are ready for this. So let's go. Faraday's first law of electrolysis. The law states that the mass of a substance that is deposited during electrolysis is directly proportional to the quantity of electricity passed through the solution. So what does this mean? This simply tells us, according to Faraday's first law of electrolysis, that if you have a solution, an electrolyte, and you pass current through the electrolyte, now the metallic ion per se that you want to be deposited at the cathode, are you following, right? The mass of that metallic ion, the mass of that metal that is going to be deposited, that is going to be discharged, that is going to be given off, that is going to be liberated at the cathode will depend on the quantity of electricity that you pass through the electrolyte. So you see here that Faraday's first law of electrolysis draws the relationship between the mass that is being discharged, that is being deposited, and the quantity of electricity passing through it. Now, if Faraday's first law says that the mass deposited is directly proportional to quantity of electricity, we can use mathematics direct proportion of variation knowledge to set out what this equation should be. And so come with me as we analyze that on the board. Is that okay? Faraday's first law of electrolysis states that mass is directly proportional to quantity of electricity. Now, if we are to remove the proportionality sign, which of course you know that is what has to be done for us to be able to solve problems on this will give us that mass is equal to some constant of proportionality multiplied by that Q, the quantity of electricity. So we have, good. Now you notice that we've introduced a constant and have decided to use Z for the constant. Please take note that even in physics, you deal with this. In chemistry, you deal with this also. Are you following, right? The Z there is called the electrochemical equivalent, ECE. Z is equal to electrochemical equivalent, ECE. Good. And the electrochemical equivalent for a particular cell is specific for that solution. Is that okay? Alright, let us look at this Q, the quantity of electricity. M there is mass. Q, which is quantity of electricity, it's important for you to know that it is equal to the current that you are passing through the electrolyte multiplied by the time it takes for the current to pass during the electrolysis. Therefore, our Q will simply be IT if I use I to be current and T to be time. So we now have this, that quantity of electricity is equal to IT, current times time. Are you following, right? If we substitute this equation 2 in 1, we are going to get that the mass deposited, discharged during electrolysis will be ZIT. Okay, where the Z, of course, is electrochemical equivalent, I said. The implication, N is equal to ZIT. Where this IT is the quantity of what? Electricity that is passed through that solution during electrolysis. Okay, so this is great. It's wonderful. Your examiner can ask you to find the mass deposited, can ask you to find the current. The examiner can also ask you to find the time. In general, the electrochemical equivalent for the electrolyte is usually given. Okay? Now, I want to say this. How do we apply this to solving problems? Are you following, right? Specifically, maybe in the case of chemistry. In the case of physics, most times the question, come a bit straightforward. But for chemistry, we would have to introduce something very important. Even though in physics, your examiner can also give you that concept. But what I'm trying to say is, this concept of the Faraday, okay, is used more. That's the next thing I'm going to, explain. Is used more in chemistry. Are you following, right? Where we talk about the value of 1 Faraday in terms of quantity of electricity. But before I do that, I would like us to consider this half-cell reaction equation, okay? It's going to be a reduction reaction, which means reaction that takes place at the cathode. I am going to give 3 quick half-cell cathodic reaction equation, depending on the valency of the metal that is going to be deposited. We're going to check for that, which is univalent. We're going to check for divalent metal, and I will also show you for trivalent metal. So we shall use the concept of silver. I'm going to target more of metals that questions are usually being based on. Silver for univalent. I'm not saying it's only the ones I'm going to give anyway, but oftentimes, okay, if you're talking about univalent ions, positive ions, Usually questions are drawn from the area of silver, because silver is univalent. Sodium too is univalent, but most times you're not being tested on sodium content. Okay, so I'm going to show the cathodic half-cell reaction equation, okay, for silver, where we'll be dealing with univalent ion. I would give you that of copper, where we'll be dealing with divalent, and of course aluminium. So watch. At the cathode, assuming that during electrolysis, you are electrolyzing a solution of silver, say silver trioxonitrate 5, AgNO3 solution. We expect that silver will be deposited at the cathode. And like I told you, at the cathode, reduction reaction takes place there. So you have silver, which is in solution. Because silver is in solution, it's going to be written with its valency, its oxidation state, which is positive 1. I'm going to introduce aqueous here because this is silver system. Now what happens at the cathode? This silver is going to pick one electron in order to be deposited as silver metal. Take note that this plus simply shows that silver originally, are you following, right? When it reacted to form silver nitrate, it gave up one electron. That's the meaning of this. Now, if silver is to be deposited at the cathode, at that cathode is going to pick that electron. Are you getting me, right? So what is going to happen? I'm going to write plus electron here. This is one electron. Once silver picks this one electron, it's going to be deposited as silver metal, a solid. Okay? Now, I want to tell you something about the number of Faraday that will deposit this silver. Because generally, whenever electrolysis process takes place, the metal will be given off, will be discharged as a solid at the cathode. I've explained that already. And because the metal is discharged at the cathode, we say that 1 mole of that metal is always given off. 1 mole. And remember, please, that 1 mole of every substance, okay, is equal to the relative atomic mass of that substance. For example, silver is 108. 108, that's the relative atomic mass. Are you following, right? So this reaction you're seeing here, deposited, this is 1 mole of silver, which is equivalent to what? 108 grams, okay, of silver. So what do we do there? The implication, how many electrons was picked by silver? 1, because silver is univalent. So we can now interpret that to mean that 1 Faraday, that 1 electron means 1 Faraday gave up 1 mole of silver, discharged 1 mole of silver from the solution. And 1 mole of silver is 108 grams. So I will write that 1 Faraday, 1F, is equivalent to 1 mole of silver. 1 mole of silver. And 1 mole of silver is 108. So I'll put it in brackets. 108 grams of silver metal. Are you following, right? So you want to have this is a standard. It is what? A standard. Any univalent ion that is being electrolyzed to deposit that metal, if it's a positive metal, are you following, right? It is expected for you to know that 1 Faraday, because being a univalent substance, it will require 1 Faraday to deposit 1 mole of that metal. So in the case of silver, 1 mole is 108 grams. Let us assume that maybe it is potassium solution, for example. So maybe it is, okay, sodium solution. You electrolyze sodium chloride, for example, and then sodium is deposited at the cathode. What would say sodium is univalent, positive 1. So we'll just write that 1 Faraday, it will follow this reaction. In place of silver, you have sodium, then plus, positive, univalent, plus 1 electron. Then sodium metal will be discharged. Then as a standard, we'll establish that 1 Faraday produces 1 mole of sodium metal. And 1 mole of sodium metal, the relative atomic mass is 23 grams. Do you get that right? 23 grams in that case. Alright, now that we know what this 1 Faraday is going to produce for this silver, I'm using silver as just an example. It could be any univalent metal. This 1 Faraday has an equivalent. 1 Faraday is equal to 96,500 coulomb of electricity, which means that the quantity of electricity in 1 Faraday is equal to 96,500 coulomb. It's a standard. You see this cube? Quantity of electricity which is equal to current times time. For every 1 Faraday, this current times time value is 96,500. So I can just come here and maybe in brackets, I would write 1 Faraday is equivalent to 96,500. So in bracket, 96,500 coulomb. 500 coulomb. So that will produce that will discharge, that will deposit 1 mole of a univalent ion or a univalent metal. So with this now, your examiner can ask you anything, and then maybe can ask you, okay, you know this as a standard. If you pass a current of, let's say 5 ampere through the solution for, let's say, 30 seconds, what mass will be deposited? 5 ampere current is now passed through the solution in 30 seconds. You know that current of 5 and time of 30 seconds will give you a quantity of electricity. 5 times 30. Are you following, right? Which is going to give you 150 coulomb. So your examiner might now ask you, under that condition of current of 5 ampere and time of maybe 30, are you following second? These are just examples. What mass can be deposited? Which means you're going to fix 150 coulomb there equal to, you don't know, say maybe X. That X will now be the mass that is deposited for a current of 5 ampere and 30 second time. Don't worry, when we solve question, you grab that. Remember from this equation, okay, let's say equation 3, you can be asked to calculate either the mass deposited, the current, or the time. In any case, the examiner will give you the other quantities value. Are you getting me right? Okay, we are moving on. Let us check for that of divalent metal. Copper, I told you I'm going to use as an example. So we have something like this. Since copper is divalent, are you following, right? It means at the cathode, copper will need 2 electrons. If you pick 2 electrons to be discharged as copper solid. So this is going to be 2 electrons, and then we have copper metal discharge. Now these 2 electrons will be equivalent to how many Faraday? If 1 electron is 1 Faraday, 2 electrons is definitely 2 Faraday, which means every divalent ion, are you following, divalent metal, will require 2 Faraday to deposit 1 mole of it, which is equal to a relative atomic mass of it. So we go, from here we know as a standard that 2 Faraday, and 2 Faraday in bracket will be 2000, okay, will be 2 times 96,500. 2 Faraday will be 2 times 96,500 coulomb. That is expected to discharge 1 mole of this metal. And 1 mole, we are using copper as an example. 1 mole of copper is there about 64 grams. So I'm going to have this 64 gram. Okay? So this becomes a standard. 96,500 times 2. If you press it down, you know, going to get a value there about 193,000 or so. Okay? So 2 Faraday will give you this coulomb. The quantity of electricity in 2 Faraday is this value. Multiply that, like I said, you find the value, okay? 2 times 96,500 should give us 193,000 coulomb. This quantity of electricity, Q equal to IT. The value of this quantity that is inside 2 Faraday is this value. So that your examiner can now ask you, okay, if you know as a standard for divalent metal, this is what is expected. Let me think of another divalent metal, zinc, instead of copper. It will follow this process. Zinc 2 plus 2 electrons are expected to be picked, so that zinc metal will be deposited at the cathode. And of course, you can now write 2 Faraday, which is equivalent to so number of coulomb here, will be equal to 1 mole of zinc. Then 1 mole of zinc, I guess, is there about 65 gram. Are you getting right? There about 65 gram or so. Of course, that relative atomic mass ought to be given to you by your examiner, so I don't see that as much of a problem. Which means in the case of zinc, you set that standard out. 2 Faraday, which is this quantity of electricity, will produce 1 mole of zinc, which is equivalent to there about 65 gram, I said. Therefore, if your examiner now asks you, if you know that as a standard, what if you pass a current of, your examiner gives you the value of the current, and the time during which the current passed. Okay, let's assume that current of 2 ampere, and that it passed for 1 hour. 1 hour is 3,600 seconds. It means you're going to do, okay, 2 times 3,600 seconds, which will produce a quantity of electricity for you, current times time. Under that condition of current 2 ampere and the electrolysis being run for 1 hour, which is 3,600 seconds, you multiply 2 times 3,600 seconds to calculate the quantity of electricity there. What mass of the divalent metal will be discharged at the cathode? Please take note, it's not always compulsory that it is mass you'll be asked to find. Your examiner can still choose to say, okay, you know this as a standard, fine. What current would you need to pass through the electrolyte, say maybe in that 1 hour, to discharge you're not giving a particular mass, maybe to discharge something like 30 grams of that metal. In that case, it will be current, you don't know, I times T, the time, 1 hour, which is 3,600 seconds, equal to, then the mass given to you, I assume 30, which means the unknown will be current. Cross multiply and then you solve, you get your result. Okay, we move on for trivalent metal ion. This is going to require 3 electrons, and then it will be discharged as aluminium solid. It still follows the same pattern. How many Faraday do we need to discharge this 1 mole of aluminium at the cathode? We require 3 Faradays, and 3 Faradays is 3 times 96,500 coulomb of electricity. Okay, and we expect that this will deposit 1 mole of aluminium. 1 mole of aluminium is there about 27 grams. Are you following, right? So this is the standard in the case of aluminium as a trivalent. The examiner might choose to give you any other trivalent metal instead of aluminium. But like I said, in most cases, these guys, silver, copper, 2 ion, aluminium, 3 ion, they are usually being a kind of, questions are usually based on them. That does not mean that you can't be tried on other metals. So it's just for you to know the oxidation number of that metal or the valency. So in the same way as I analyze, once you have this as your standard, your examiner can now test you on anything. For example, in this case, if your examiner wants you to find time, the examiner can now ask you if a current of, let us say, 10 ampere is passed through this solution, and let us assume that 54 grams of aluminium is deposited. What time will it take for this electrolysis? So you see, in that case, you know the current, you don't know the time, you know the mass deposited under that condition of current of maybe 10 ampere and an unknown time. You are not expected to calculate that time that will be able to produce a given quantity of electricity that can deposit, say, 54 grams of aluminium. But this will be the standard for that aluminium. Alright, let us move on quickly to talk about the second law of electrolysis by Faraday. Okay, but I want to say this. Understanding first law very well, second law is just simple. So let us state second law of electrolysis by Faraday. Faraday's second law of electrolysis states that if the same quantity of electricity is passed through solutions of different electrolytes, the relative number of moles or mass of the metals deposited will be inversely proportional to the charge of that metal. So what is the point of Faraday's second law of electrolysis? Now you have 2 solutions. These are 2 solutions of different electrolytes. And you're now required to pass the same quantity of electricity through them. Let us assume that this is a univalent solution, a univalent metallic solution. And this one is, let us say, a trivalent metallic solution. It can be divalent. All we know is that these 2 solutions are different. And the charge of the ions there are also different. Like I said, if this is univalent, it will be positive 1. If this is trivalent, it will be positive 3. Or if it is trivalent, if it is divalent, it will be positive 2. So Faraday is now saying, in his second law, that if you pass the same quantity of electricity through these 2 different solutions, the moles, the number of moles that will be deposited, or otherwise the mass of each of them that will be deposited, even though the quantity of electricity you pass through them is the same, but the mass you are going to obtain will be different. The mass you are going to obtain, the value, will be inversely proportional to the charge of these ions. You know, the concept of inversely proportional, what does it mean? As one is increasing, the other is what? Decreasing. Which means generally that the one that has, let us say, a lower charge, more of its mass will be produced. Like if this is univalent, then more mole of this will be produced, more or higher mass of this will be discharged. And if this is trivalent, if you compare the mass that is going to be discharged, it will be less than this. Because the law said that the mass or the number of moles that will be discharged in this case will be inversely proportional to the charge of the ions. So think, for example, let me just use numbers to explain this concept. Imagine you are passing, let's say, 100 coulomb of electricity through these 2 solutions. This is univalent, this is trivalent. If the mass of this univalent deposited is, let us say, 15 grams, the mass of this trivalent or divalent, as the case might be, should be less than the 15 gram. Are you following? Because the charge of this guy is greater than the charge of this one. This is tri, and this is what? Uni. So the mass of this, if it is 15 gram, then the mass of this one, the trivalent or the divalent, should be less than this. So let us assume that maybe 10 gram of this will be deposited. Okay? Because this one has higher charge, lower mass will be deposited. This one has lower charge, higher mass will be what? Deposited. As long as you pass the same quantity of electricity through them. So I'm just going to write a summary of this Faraday's second law of electrolysis. The truth of the matter is, when we solve questions on it, it becomes much more clearer. We actually approach Faraday's second law of electrolysis calculation from Faraday's first law calculation. In our next video, I'm going to deal with the calculation of this, then you see how we do that. We'll look at questions on first law, questions on second law of electrolysis. But generally, according to the second law of electrolysis, we are saying that the mass deposited will be inversely proportional to, inverse proportion is 1 over the charge of the ion. So it means that an ion that has higher charge, the mass that will be deposited will be low. And an ion that has lower charge, the mass deposited will be high if you pass the same quantity of electricity through them. Okay? So generally, the one thing we do in that second law is to determine that quantity of electricity which is the same for both. If we determine that quantity of electricity, the problem is solved. We can now break the question into 2 parts, okay, to solve it. Alright. So this is the summary of the concept of electrolysis in terms of Faraday's laws of electrolysis. In my next video lesson, I am going to deal with the calculations of these laws of electrolysis, okay, and then we'll see how we apply what we've learned from this video lesson. So I encourage you to watch this video lesson. If you have any question, please feel free to make use of the comment section, and I'll be right there to respond. Share this video so that other scholars like you will see it, and of course watch the video lesson and learn the concept of electrolysis. Before I forget, please, it's also very important that we get to know the concept of the electrochemical series, also called the activity series or redox series. Okay, I think it starts with potassium, and of course to calcium, to sodium. Please just watch the screen and you will see this series, displaying. It is expected that you try to memorize that. It's going to help you a lot. The series, the metal ions are actually arranged in decreasing order of their electropositivity value. Alright, hope to see you in my next video lesson. Please remember to subscribe if you've not subscribed to JAMB41's YouTube channel, and please give us a like. You can leave a comment and we'll appreciate that, okay? Alright, do have fun with your study. See you in my next video lesson.